And this presentation is about the policy recommendations that are currently being developed for the World Bank to ensure sustainable development of dams and reservoirs. As an overview, the objective of the World Bank is to alleviate poverty and through sustainable development. And in this case, we are focusing on sediment management to ensure a reliable supply of water from reservoirs for industrial and domestic use, for power generation, food production, and for flood management. So we focus on sediment management, and we do it in a way that encourages the sediment continuity in rivers, which leads to a win-win situation by preserving reservoir storage and concurrently preserving the river morphology and aquatic health downstream. The third component is to change the behavior of economists, engineers, and operators and developers to accept this policy and then implement it. There are two essential components then of this policy. The one is to develop the policy recommendations through principles that will ensure that engineers and economists and operators perform in a way that ensures sustainable development of dams and reservoirs that will preserve the environment and provide social benefit. And the second component is changing minds, that is research in cognitive psychology. And the whole idea is to understand why there is cognitive dissonance with developers, politicians, economists, and engineers. And what that means is, why do they think in the short term, while dams and reservoirs really are infrastructure that has a long-term existence? So the core values that we use for this development of these policies is firstly to ensure that we all have a correct understanding of the meaning of sustainable development and how we apply that to dams and reservoirs to meet these policy objectives. And it really comes down to harmonizing engineering, economics, and environmental aspects of projects to ensure social well-being. This is very important. So let's look at each one of these. First, what is sustainable development? And sustainable development is best defined by the Brundtland Commission report. And it says that sustainable development seeks to meet the needs and aspirations of the present without compromising the ability to meet those of the future. So this is really a very succinct but a very powerful definition. And what it really means is that we should strive to create intergenerational equity. This is a very important concept. And what that means is that we should develop infrastructure in a manner that creates fairness between generations. And what it implies is that environmental stabilization is a desirable consequence of sustainable development. It's not the objective. So what you'll see is here I use the term sustainable development and not sustainability, because sustainability has various meanings for various people, but what we are dealing with is sustainable development. So if we want to summarize it succinctly, sustainable development means harmonizing the engineering, economic and environmental aspects of projects to create intergenerational equity. That's the focus, to create intergenerational equity, that is social well-being in the long term. So once we know what sustainable development means, what we infer by that if we use the term, the next is to discuss how we sustainably develop a resource. And as you know, there are two kinds of resources. There are renewable resources and exhaustible resources. And exhaustible resources like mining, we cannot develop in a sustainable manner. But renewable resources like, for example, cultivating wheat, we can. And the concept is that if we use the renewable resource at a rate that is smaller than the rate of regeneration, then we can develop it in a sustainable manner. So let's then ask the question first, is fresh water a renewable or an exhaustible resource? And to get some idea of how much water there is on Earth, we can compare the diameter of the Earth to the diameter of spheres that we use to place water in. So if you place all the water on Earth, everything, into a sphere, it'll have a diameter of 1,383 kilometers, compared to the diameter of the Earth, which is 12,756 kilometers. And that is an exhaustible resource because there's only so much water. But if we look at fresh water and we place all the fresh groundwater on Earth, accessible fresh groundwater, in a sphere, it has a diameter of about 69 kilometers. And the other resource, river water, if we would place all the river water on Earth into a sphere, it will fill a sphere with a diameter of only 16 kilometers. That's most probably less than what most people drive to work on a daily basis. But the good news is that is a renewable resource because of the hydrologic cycle. So the next question that we need to ask is which one of these two resources, groundwater or surface water, has the greatest potential for sustainable development. So what we need to do is then compare the rate of usage to the rate of replenishment. And a proxy that we can use for the rate of replenishment is the residence time of water in these resources. That's the time it takes for a drop of water to move from the upstream end to the downstream end of the resource. So if you look at all the fresh accessible groundwater on Earth, the residence time for that is 1,400 years. Looked at it differently, if we would be able to suddenly, in an instant, remove all fresh groundwater on Earth, it'll take 1,400 years for it to replenish. On the other hand, the residence time of river water is 16 to 18 days. So if you would remove all the river water on Earth in an instant, it will be replenished in about 2 weeks. And if we then compare that to the rate of usage, we can conclude that the replenishment rate of groundwater is much longer than the usage rate, and that the replenishment rate of river water is roughly on the same time scale. So just from a visceral point of view, we can conclude that river water must probably have the greatest potential for sustainable development. And that has been proven to be true by research at the University of Utrecht and McGill University in Canada, where they looked at all the large aquifers on Earth, and the golden ones here are the ones that are overutilized. And they came up with this concept of a groundwater footprint. And what it really means, for example, in the case of the upper Ganges on the lower right corner, the groundwater footprint for the upper Ganges is 54. And what that means is that on an annual basis, they remove 54 times more water from the aquifer than what's replenished annually. And if we look globally, the global groundwater footprint is 3.5. What it means is globally, we use 3.5 times more groundwater than what's replenished on an annual basis. So the conclusion is that we'd rather focus on rivers for sustainable development. It has a much greater potential. But obviously, as you know, is that rivers, the flow in rivers is not constant. And this hydrograph here, each one bar is the annual flow in this river, and the red line is the long-term mean annual flow of the river. So, for example, you'll notice that here is a period of about 11 years where the annual flows are less than the long-term mean annual flow. And if you want to supply water out of this river, you must provide storage that is very large and can span multiple years. Now, originating from South Africa myself, you know that there are multiple year droughts, and this is a problem you often deal with. So the next question is then, if we're now facing climate change, how is that going to how is that going to influence our infrastructure development? Now, this map of mean changes in mean annual flow is very well known, and you'll see, for example, in the case of South Africa, they expect a reduction. But in other places, there are more water. But that is not really the main issue we need to look at. The main issue is that climate change will introduce hydrologic variability, and that will increase globally. Okay. So the question is then, how is that going to influence our water supply, our ability to reliably supply fresh water? So what I have here on the left side is a map of the world with estimates of the areas of the world that experience multiple year droughts, that are droughts of 2 years or longer. Okay. And what I did is I just did an analysis. I just say, let's just assume that the hydrologic variability worldwide increases by 25%. What will happen then? Okay. It's just a test to see what is the impact on multiple year droughts. And if we draw that map, you see that larger parts of the world will experience multiple year droughts. In the case of Africa, which has mainly a big problem with multiple year droughts, what will happen in many places is that the intensity of these droughts will increase. So how do we prepare for this? And what one can do is to draw a graph of yield, that's the amount of water you can get out of a river, and hydrologic variability. Hydrologic variability is the proxy for climate change. And if we create a dam with a reservoir of about 60% of the mean annual flow, you can see that if climate change takes place, say that the hydrologic variability changes from 0.3 to 0.6, and the hydrologic variability is represented by the coefficient of variation of annual flows. You see that there's a significant drop in the reliable yield that we can obtain from this reservoir. If we make the reservoir volume larger, the reduction is much less. And if we make it very large, like say 2 times the mean annual flow, you can see there's a very small change in the amount of water we can reliably supply due to this increase in hydrologic variability. And again, hydrologic variability is represented by the annual coefficient of variation of the flows. So the answer to this is that we need large reservoir storage to provide resilience in our water supply systems. But then, as you know, and this is what this symposium is about, is that sediment is the enemy of reservoir storage, and it diminishes reservoir storage in reservoirs. This is a big problem. So let's then look at the combined effect of climate change and reservoir sedimentation. So we have the same graph of yield versus coefficient of variation. The coefficient of variation represents it's a proxy for climate change. So say we start with a reservoir, just for argument's sake, that has a volume of 2 times the mean annual flow. And we can supply, we have a coefficient of variation of about 0.4, which is common. And we see that we can supply about 95% of the mean annual flow on a reliable basis. But then if climate change occurs, and say the coefficient of variation changes from 0.4 to 0.6, there is a small change in the amount of water that we can reliably supply. But if through sedimentation, this reservoir results in a reservoir volume of 0.6 times the mean annual flow, you can see that the combined impact of climate change and reservoir sedimentation is significant. Okay. So if that is the case, and we know that we need reservoir storage and we have sedimentation affecting it, let's look at what happens globally to reservoir volumes. So firstly, this is a graph, that dark line is a graph of reservoir storage that was created through construction of dams from 1900 to 2020. And you see there's a continuous increase of it. But if we allow for reservoir sedimentation, the storage loss is estimated as being somewhere between 0.8% and 1% per year annually for global storage. You'll notice that the net storage reduces significantly. So, and actually what is alarming is that the net storage, we're losing more storage than what we are constructing through new dams. Okay, so we are in a negative territory. And if we now additionally look at population growth and we calculate the reservoir storage per capita, you see that dotted curve, we are now in a situation where we were last in the 1960s. So we are really regressing in terms of the global storage we have available for reliable supply of water. And this is no unknown situation for you. You've had these droughts in Cape Town, 2015 to 2018, and I will not talk more about that. You know more about it than what I do, but that is essentially a long-term drought that you've experienced there with almost dire consequences. So what do? We can implement sediment management technology. And in this talk, I'm not going to expand on that because this is really the topic of your symposium. But one way to categorize it is that one can do catchment management. So you can try and reduce the amount of sediment flowing into reservoirs. We can implement sediment routing by trying to either move sediment through a reservoir or around the reservoir and preventing deposition of sediment in the reservoir. And the third category is to remove sediment that has already been deposited. But these techniques are not generally implemented, as you know. And the question is, why is it not implemented? And the reason is that our paradigm for the development and design is incorrect. In general, what happens is that we adopt a design life concept in engineering design and economic analysis. And we think of reservoirs as being exhaustible resources. Now, the design life concept is good for other civil infrastructure, like, for example, highways. You know, we can design a highway, say, for a design life of 30 years. And after 30 years, we come back, we resurface it, and we can essentially use it in perpetuity. So if we can use it in perpetuity, what we have done is we have sustainably developed that highway because it is there for multiple use, an intergenerational equity has been developed. But in the case of reservoirs, if a reservoir is filled with sediment, there's virtually nothing we can do. It is a lost cause. So this design life concept is something we need to get rid of when it comes to design of dams. And the essence is to look at a life cycle management concept. So what is the correct understanding of a reservoir? Is it a renewable resource or an exhaustible resource? Okay. So if we really look at it, when we build a dam, we create a reservoir upstream of it. It's a storage space. And this storage space can either be renewable or exhaustible. But the neat thing about reservoir storage is that it really has a dual nature. And its actual assignment of its character depends on what we do as designers and economists. Okay? If we design the facility to be able to retain reservoir storage in the long term, we can classified as a renewable resource. But if we design them to be filled with sediment, as is currently the paradigm, then we classify it as an exhaustible resource. So that's really a decision that we make. Okay, this is an important concept. So then if we now look internationally at sediment management policy, we find that there's only a few countries that actually have policy or have techniques, engineering techniques that focuses on preserving reservoir storage. Okay, so this map, the white spaces is places where we do not have data. The dark blue are countries that do not have a policy on reservoir sedimentation management. And the green spaces are countries that have policies or have engineering techniques that are regularly implemented to manage sediment and reservoirs. So this is obviously something that needs to be corrected and that the World Bank focuses on. So the recommendations in this policy that we're developing are the following. Firstly, we focus on the assessment, prioritization, and scheduling of existing infrastructure. Okay. What is the status of existing infrastructure? Where can sediment management be successfully implemented? And then what is the economic situation? Okay. An economic evaluation of these facilities is very important. In the past, and that's one of the reasons why reservoirs are not sustainably managed at the moment, one of the reasons is that we're using a discount approach. We discount future expenses and benefits to get a present value. And if we, for example, use a discount rate of, say, 10%, then whatever happens after 30 years, the present value of that is insignificant. So we are not looking in the long term. Now, to correct this and to assist you in developing these assessments and prioritizations and scheduling, Dr. Efthimio will talk about the RESCON 2 software that we developed for the World Bank that will help you at policy level to execute this and also to look at all these problems that we are encountering. Then we will give some engineering guidance on reservoir sedimentation management. We'll give operational guidance and look at environmental aspects and ensure that we're creating intergenerational equity to ensure that we have social benefit. Obviously, monitoring is important. And the second aspect is changing minds. And currently, there are still negotiations with MBED at the World Bank. It's a cognitive psychology group and the University of Virginia to do research, to figure out why is there cognitive dissonance with policymakers, engineers, economists, and operators. Why do they think in the short term, while the infrastructure they develop lasts for hundreds of years? Okay. So that is bring us to the key takeaways. Firstly, we looked at the effects of climate change and a growing world population and concluded that we need a lot of storage to reliably supply water and perform the other duties that reservoirs provide. Secondly, we noted that reservoir sedimentation reduces storage, and importantly, we concluded that the loss of reservoir storage on an annual basis is greater than the amount of storage that we provide by building new dams and reservoirs. Thirdly, we need to look at the development of long-lived infrastructure by changing paradigms for developers, economists, and engineers. And what it is, we need to move away from the design life concept, which is often very short, and we should move more towards a life cycle management concept. And then the objective is to implement sediment management technology to reach the goals of sustainable development, which is in essence creation of intergenerational equity. That is a very important concept. And then lastly, we shared with you that we'll be doing some research on cognitive psychology to understand how we can change minds to accomplish these goals. And these recommendations are intended for use by policy developers. And this is to ensure that we have sustainable development of dams and reservoirs through reservoir sedimentation management. So I hope this is a valuable piece of information for you, and I wish you the best on the remainder of your symposium. Thank you.